Good afternoon, everyone. Today we have a talk by Dr. Paul Herman Balduf. Paul is a postdoc at the moment at the University of Waterloo and also at the Perimeter Institute. And unfortunately, soon he will be changing universities. So Paul studied physics in Lund, Jena, and Berlin, and he made his PhD at Humboldt-Universität zu Berlin under the supervision of Dirk Kreimer. And he is working in renormalization, non-perturbative effects, and combinatorics and numerics. And today we will hear his talk on graph theory and Feynman integrals. Please welcome Paul.
Thank you very much. Impressive that you can memorize all these details. Okay, so nice to see so many people here, despite being kind of holiday season or summer term, being interested in cookies, graph theory, and Feynman integrals. Of these three, I think two don't need explanation. So we all are experts in graph theory, you probably more than I, and surely we are all experts in cookies. Feynman integrals are the physics background of this talk. And I will start the talk by talking a little bit about physics. Those of you who are fine with just, getting something defined and working with it, you can safely sleep during the physics part, or you can use the time to sign up for Mastodon, which is the leading elephant-themed social network. So it's a little bit like Twitter, but with elephants. Okay, let's get started. So we're going to start very basic. In principle, what we're doing is quantum field theory, so I wanted to start with what is even a free field theory, a classical one. So a field here obviously is a physical field, so it's not a field in the mathematical sense, but it's a quantity that depends on position and time. And if you ask a first-year physics student, they often say something like, oh, the field will behave such that it minimizes energy, but that's not what it does because, energy is conserved, so you can't minimize energy in such a setting. Instead, it will assume a state where the action is stationary, or in general, the action is minimal. And the action density is this Lagrangian density. And I think everyone who is either in physics or in optimization knows very well how to find the point of stationary Lagrangian function. Well, essentially you need its first variation, so the first derivative, which gives you an equation like this Euler-Lagrange equation. And you find for your classical free field this equation of motion. Now, why is that a free field? It is a free field because it's linear in the field variable. So if you have a solution of this is a wave equation, so a solution would be a plane wave. If you have two plane waves and add them up, you still get a solution. So these plane waves don't interact at all. That's what it means to be a free field. And I'm telling you this to appreciate what it means to be an interacting field. Namely, the field is interacting as soon as it has in its Lagrangian a term which is higher than quadratic. And, well, you can write a lot of things. In principle, for this talk, we are only ever going to consider this particular Lagrangian, which is creatively called phi-4 theory, because it has a fourth power in its phi. So the field variable is phi, and it has a fourth power. And we have here one parameter, this lambda. This is, well, in physics, it's called a coupling constant. So when it's 0, we are back to the free field case, and when it's non-zero, we have this phi-4 type interaction. And now you have a certain freedom of whether that lives in some space, whatever, and we will only consider ordinary four-dimensional spacetime. So there's 3 space dimensions and 1 time dimension. Now that was classical field theory. Now let's do a 1-minute crash course in quantum field theory. The only difference is, okay, there are a lot of differences, but one crucial difference is that instead of minimizing the action, we actually allow all the fields to exist simultaneously, but we want to weight them with this exponential factor. So we weight them by their exponential action. Here the constant h bar is the Planck constant, so this is the smallest unit of action you can have. And there is an I in here which makes all the mathematics more complicated, but we're going to ignore that. And the fact that we don't have just one field, but this weird superposition state, means that, well, the solution we are looking for is not actually a function of space and time anymore, but rather we are looking for correlation functions. So they in principle look like this. So I use these angle brackets to indicate expectation. So this would be an expectation of the field variable at k distinct points. And similar to the classical field, the free solution can relatively easily be found. In the classical case, we had plane waves at the free solution, and here now...
I'm not sure I understand that notation.
Yes.
So it's the integral of that phi of x1 to phi of xk?
Here? Or where? This integral, you mean?
The inner product phi of x1.
This.
I don't understand that notation. Sorry.
Yes. Okay. So physically what we want is, we want an expectation of that. So if you view it as a, well, it depends a little bit exactly what setup you need. In principle, you would want your field weighted by this factor, and then you integrate over the field, which is this functional integral, which is notoriously ill-defined, but something like that. And then in the integral, you will have all these factors. But yeah, I skipped that because it's mathematically sometimes a bit fishy to actually write these formulas. Yes, and the 2-point function of the free field is called a propagator here. So this is what replaces the plane wave solutions of the classical theory. And now if we want to solve an interacting field theory, again, we can't do that analytically. Instead, we're going to use perturbation theory, which very schematically means we expand this exponential function as a power series in the coupling parameter lambda. There are a lot of details here which I'm sweeping under the rug, but in principle, we get the interacting correlation functions as a power series in lambda. And we notice that this interaction is such that it involves 4 powers of the field at the same point in space and time. So that's what's called a local interaction, as opposed to other things that you could potentially write down. And that lends itself very much to a graphical notation. Namely, if you have 1 power of lambda, you will have one of these phi-4 terms. So naturally, you have an interaction at only 1 point in space-time here. If you have order lambda squared in your series, you will have 2 of these interaction points, and so on. So you can kind of organize the possible interactions in terms of these graphs. They're called Feynman graphs from 1949. And yeah, these are not all the Feynman graphs. They also, each of them has different orientations. There are also graphs that are non-connected and whatnot. So there is much more. But these are the first interesting ones, I would say. And we notice that the first one is just a tree, and then you start to get cycles. And these cycles are called loops in physics. And what's called loops in math is called tadpole in physics. So we're going to graduate our graphs by the loop number. So this is a 1-loop graph, this is a 2-loop graph, and so on. And these are independent loops, so it's dimension of cycle space. Okay, now we have these pictures. So far, so good. But to actually compute something, we need to take into account that this interaction can happen at any point. So we need to integrate over the location of these interaction points. And that gives us Feynman integrals. Now the thing is that if you actually do an experiment in quantum field theory, you typically do a scattering experiment where you have particles which are being collided, and like you're not measuring the position of particles, but you're measuring their momenta and directions and so on. So it would be much more convenient to have this as a function of momenta. That's why you do a Fourier transform and usually consider these functions as function of momenta of the external particles and not of positions. Okay, so that was the physics background. So the general idea of this talk is we want to understand the typical properties of Feynman integrals. Okay, now let's start the actual definitions. So a Feynman integral, as I said, can depend on momenta and whatnot. So on a lot of quantities, it's in general a complicated function. To avoid all these complications, we're gonna concentrate on the absolute simplest case, which is vertex-type graphs which are without 2 and 4 valence subgraphs in our 4 regular theory. That means that these graphs are primitive in the Hopf algebra of Feynman graphs, so they don't have subgraphs of the same type, essentially. They have 4 external edges themselves, but no subgraph has. And also, we will ignore the dependence on masses and the dependence on the angles of the incoming and outgoing particles and only concentrate on the dependence on the overall energy scale which is typically a ratio between your momentum squared and some reference momentum or logarithm or whatever. And it turns out that for these particular primitive graphs, the Feynman integral evaluates to L-independent terms, so terms that depend only on angles. And the entire L dependence is given by a single number. And this number is called the period. And so it's given by this integral, so it's actually a period in the sense of Kontsevich and Saget, so it's an integral over a rational function with rational boundaries. This rational function here is the semantic polynomial, which is the dual Kirchhoff polynomial of the graph. And our class of graph is such that this is guaranteed to be finite. So it's some real number. And this is the only type of Feynman integral we're going to consider in this talk. So here's an example. The very first period. We have this graph, and the semantic polynomial, like the Kirchhoff polynomial, is given by a sum over spanning trees. This graph has two spanning trees. One is this edge. The variable not in the tree is then A2, or this edge is the other tree, and not in the tree is A1. So this is our semantic polynomial, and we just plug it into the integral, and we find that this delta function simplifies it a lot. Actually, it's an integral over 1 divided by 1, which is 1. So the period of this graph is 1. That was easy. Hopefully it goes on like this, but it doesn't. So here's loop order 2. Now we're trying to find graphs at loop order 2 which are primitive. Typical graphs you could write down are these, and there are a few more. But you will see that they have this double edge as a subgraph, and this subgraph is 4-valent. So it has these 4 external edges. And here as well we have this 4-valent subgraph. Or phrased differently, these graphs are not cyclically 6-edge connected, quite obviously. And it turns out that indeed at 2 loops in this theory there are no primitive graphs. This has a nice side effect that whenever you have a multi-edge as a subgraph, the graph is not primitive. So apart from this one example here, all our graphs are going to be simple graphs. No self-loops, no multi-edges. Okay, we have vertex-type graphs that have 4 external edges. We can glue these 4 edges together and get another 4-valent vertex. That's pretty trivial. Do it like this. Here are the 4 edges. Glue them together and get this thing. It's clear that it's unique in that direction, but it's not unique in the opposite direction. So when you take a different vertex here, decompose it, you're going to get one of these 3, and they are not isomorphic. Why am I telling you this? Because these 3 vertex-type graphs, I mean, they are non-isomorphic graphs. They have different graph polynomials and everything, but they have the same period. So if you actually solve the period integral, then you find the same number. And that is super helpful because it means that we can work with these completion-type graphs which have no external edges, and we can solve also a lot of combinatorics with these external edges. Here's a 3-loop example. The only primitive graph at 3 loops, or 5 vertices, is K5. If you decompose any of its 5 vertices, you get this guy. Give it a few names and labels. Now we want the semantic polynomial. We could enumerate the spanning trees, but of course, to do it more algorithmically, we use the matrix tree theorem. So we write down the Laplacian, which is this. We delete this, or any one column and any one row, and take the determinant of the remainder. That gives us the Kirchhoff polynomial. And then we replace every a by 1 over a and multiply by all the a's, and get the semantic polynomial, which is this relatively long polynomial for this graph. And you see that this is really the second easiest graph that exists in this theory, and it also has already this long polynomial. You want to square this polynomial and then integrate it over its 6 variables. And I'm not going to show how to do that. It can be done. People have done it in the 80s, and you find 6 zeta 3 as a value. So we learn from this that, well, first of all, we learn that Feynman integrals are interesting. They appear when you want to solve interacting theories, for example, quantum field theory. You can also use them for gravity or for statistical systems and so on. We concentrate on one particular type of graphs, namely these periods in 5-4 theory, given by this integral. And yes, so we saw already that these integrals can be very hard even for for the smallest and simplest example graphs. And our goal is to understand what they do. Okay, questions so far about definitions and background? No? Good. Okay, so let's start with a little bit more graph theory. You can give this theory an ON symmetry, and ON is really the orthogonal group on n component vectors. And that means that your field variable will be an n component vector, and the interaction term is replaced by scalar product phi dot phi squared, which clearly is phi4, but you need to organize the vector indices somehow. And if you think about this a little bit, the dot product is phi1 times phi1 plus phi2 times phi2 and so on, so it matches corresponding indices. And what that means graphically is that you replace your vertex by all ways of matching the indices. So you get something like this. And then for the entire graph, you will decompose every vertex like that. Sum over all possible decompositions, you get 3 to the number of vertices terms, quite obviously. And some of these terms will in the end form closed lines, and some will go through if your graph has external edges. Each closed line in the end corresponds to the trace of a unit matrix, so it gives you a factor n. So let's do that with our favorite example. This graph, so it has 2 vertices, hence there are 3 times 3, so 9 different ways to split. And that gives you these 9 results. If you split both vertically, you get this. If you split both horizontally, you get this. And in all other cases, you get one of the others. Now it turns out that this graph itself has 3 different orientations with respect to its external edges. If you sum over all those, what you get is something that's proportional to the vertex itself. So it's 8 times vertex plus 1 times closed loop times vertex. That happens for all vertex type graphs. And you always get some prefactor, and this loop becomes just a factor of n. So this prefactor is a polynomial in n. That's called the circuit partition polynomial. So formally, it's the decomposition of all the vertices in the graph, and then n to the power of circuits in each of the decompositions. So for our example, this polynomial was just n plus 8, but for larger graphs, it's larger. And that's all you need to do to implement this symmetry. You just multiply each graph with this polynomial, and then you have your fully ON symmetric theory. And this is going to show up later several times. This is why I introduced it here. But let's maybe first concentrate on the graphs themselves. How many graphs are there? We probably know that the number of graphs in general is very large. So here is how many we have. We know the first 3 lines here. So there's the 1 loop guy, this double edge. Then there was 0 at 2 loops. Then there was K5 at 3 loops. And then it goes on, and you get very, very many, which is clear because the number grows factorially. At 15 loops, for example, you have 1.4 billion. Now, okay, combinatorially, that's kind of clear, but it's annoying if you actually want to compute something because it means that you have to solve billions of integrals. But we know already that whenever they come from the same completion, they have the same period. So perhaps there might be lots and lots of graphs, but maybe they all have the same value. And that's not quite true, but at least there are some symmetries. So it turns out that there's a handful of operations you can do on the graph that do not change the period. So the actual number of periods is smaller than the number of graphs. One very straightforward example is planar duality. If your graph happens to be planar, you can take the dual and it has the same period. And yeah, there's a lot of others which are relatively involved in terms of what you actually do to the graph. So write another program and count the symmetries. This is what we had. Now we go to completions, and obviously there are a lot less because, well, it's clear. So we're down to 82 million here. Very few graphs are actually planar. So of these 1.4 billion, only 1 million is planar. Also, that is no surprise to someone who works with graphs, I think. These other remaining symmetries, they reduce the number somewhat. So eventually here we are down to 65 million. But you see, the big step is from here to taking completions, and then the remainder is some another 20% maybe. So upshot of this is there are lots of graphs and millions of integrals that are actually distinct and that all need to be solved. Now, when we have these millions of graphs, then maybe it's interesting to relate them to random graphs. So there is the well-known model of 4 regular random simple graphs, GN4, which has a lot of nice properties. And in particular, the asymptotic number of these random 4 regular graphs coincides to leading order with the asymptotic number of primitive graphs. So that suggests that probably this is a good model for our graphs. Clearly, not all graphs in here are actually primitive. I mean, it contains graphs which aren't even 4-edge connected, but for large n, almost all should be. The big question is then, are we, with our graphs, with let's say 20 or less vertices, are we in the asymptotic region of that? And well, you can count. So here is, for example, we expect the symmetry factor, so the size of the automorphism group, to go to 1. So typically a graph should have no non-trivial automorphisms. And all its decompletions of a given completion should all be non-isomorphic. And you can actually count that for the primitive graphs, and you find that for small graphs, obviously it is not the case, but starting from something like, well, 8 or 10 vertices here, you see very quickly convergence towards this asymptotic regime. And if you're at 16 loops, which is 18 vertices, less than 1 in 100 graph has an isomorphic decompletion. So we, at least here at, let's say, 16 loops, we are actually quite far in the asymptotic regime in that respect. But it depends on the variables. So for example, the cycle length in random graphs are Poisson distributed with this mean. So we count how many cycles we have of a given length, divide by this number, and get this plot. And we see that for small cycles, yes, this ratio is somewhat close to 1. But the larger the cycles get, clearly, well, the ratio is no longer 1, because if I have here a graph which has maybe 15 vertices, clearly it can't have cycles longer than 15 edges. So yeah, it really depends on your particular variable whether or not we are far in the asymptotic regime, but it seems that at least for some variables this is really a sensible model. Okay, back to invariance. So we saw this invariance, and it would be nice to, instead of, well, fiddle around with the graphs, it would be nice to have some quantity that you compute for the graph and that tells you, oh, the periods are going to be the same or not. And such quantities kind of exist. For example, you can count the number of 6-edge cuts. And by cuts here, I always mean a vertex-induced cut, which separates the graph into exactly 2 connected components. So these 6 edges here, if you cut them, you get 1 connected component and another one. So this is a valid 6-edge cut. And the number of 6-edge cuts, so here's another one, there is one, there is one. This thing has in total, I think, 15. The number of these cuts is an invariant. And yeah, that has been known for quite some while. And the 8-edge cuts are not invariant, but you can make them invariant if you introduce certain corrections, and potentially also the higher ones. And that's currently ongoing with Erik Panzer and Karen Yates. Another one that is quite famous in the physics community is the so-called Hebb bound. So you remember the period integral was this type of integral, 1 over square of the semantic polynomial. Now you do a tropicalization, which means you replace this polynomial by its maximum monomial for every given value of a. So that, well, you decompose this integration domain, and within each of the sectors in the integral, you only have 1 monomial. And you can solve an integral over 1 monomial. It's going to give you some rational number. So that means that you can actually compute this Hebb bound purely combinatorially. You don't actually need to do any integration anymore. The integration is all analytic. And the details are a bit technical, but in principle, you need to sum over all the subgraphs in a certain way and compute certain numbers there and sum it all up. And then you get the Hebb bound. Yes, and that thing is is interesting to physicists because that same decomposition into these so-called Hebb sectors also arises in the proof that quantum field theory is consistent and so on. So this is something that has been looked at since the 60s. There is a newer one that is related to the circuit partition polynomial. Namely, the circuit partition polynomial in principle is not invariant under these period symmetries. But if you take the derivative at n equal -2, then it is. I mean, that derivative is an integer, and that integer is invariant. And you can even replace each edge of the graph by k parallel edges, do the same thing, and you get some higher version of this Martin invariant, mk, and that also is an invariant. Yes. So, well, like Hebb bound, this is something that you can compute purely combinatorially. It doesn't require any hard integration. Okay, another short summary maybe. So we know there are many, very, very many graphs. We saw that this model of random 4 regular graph is reasonably good with respect to certain properties at least. And we also saw that not all graphs actually have distinct periods, but many have. So yes, we still need to solve millions of integrals. And we found certain invariants which can potentially tell us if periods are expected to be distinct or not. And these invariants are much easier and faster to compute than the period itself. Clearly, because otherwise they would be useless. Okay, that was the combinatorics part. Now let's move a little bit more into numbers. So there is a new numerical integration algorithm which lets you solve these period integrals. I'm not going to go into any details there. It's a Monte Carlo algorithm. You get the integral to approximately 3 or 4 significant digits within an hour, which is not bad. So you can compute several thousand. In fact, we have by now more than 2 million completed, which means 33 million of distinct vertex-type graphs, if you want to count that way. Unfortunately, that needs a lot of memory, so you can also only do it for less than 18 loops. If the graph is larger, it just doesn't fit into memory anymore. And this is what you get. So here are all the periods of 12 and 13 loops, and they are scaled to unit mean. So here's the mean. And we see that a lot of them are here. We see that 12 and 13 loops overlap. And then there are these outliers here. And the outliers for 12 are these triplet, and then there's a single one here. And for 13, they look the same. There is a triplet, there's the single one. And that pattern continues. So you basically always get a bunch of numbers here, almost all of them, and then you get these outliers which get ever more extreme. So at 14 loops, they would be over here somewhere, and at 15 and 16, and it just gets worse. So this distribution looks nice, but it has a very large standard deviation, which is approximately as large as the mean itself. Here's the continuous part. It looks a bit like gamma or log normal, but it isn't actually if you look closer. But you can model it. Here is a somewhat curious observation where I have no idea why that is. If you plot, instead of the period itself, you plot 1 over square root period, you get this thing, which, if you go to larger and larger graphs, becomes more and more like a normal distribution. So if anyone has any intuition why that should happen, feel free to tell me. Yes, and it's at 1 over square root quite precisely. So you can try other powers, and it doesn't happen there. It's only when the power is actually -1/2. Yeah, the mean also gets larger a lot as the graphs get larger. And yeah, there is some old conjecture from the physics literature from the 80s about how this mean should scale, and we find that in principle it does. So there might be some offset in this constant, but at least the growth is as expected. So you see a typical graph at 18 loops here has a period in the like 10 to the 5 or 10 to the 6 region. So these numbers get relatively large. Now we saw these outlier graphs, and here they are. So this is the worst one, the one that is far off, and then these 3 are the triplet. And you see that they have a particular structure, so they don't look random at all. So this is known as the zigzag graph. So it's a 1-2 circle end. And these are kind of small perturbations of zigzag graphs. And this pattern continues to all other loop orders. So if you have larger graphs, you just have longer zigzag rings. but you always have these 4 as the 4 largest ones. And, well, that, of course, motivates the question, now, if we know that the zigzag is always the largest one, can we maybe tell from the graph alone what the period is going to be, maybe at least approximately, without actually computing anything? So, is the period correlated with some simple graph property? And to examine this a little bit more systematically, well, we considered a lot of properties, and we computed this quantity delta, which is the standard deviation of the ratio between the actual period and the approximation. So this is just a measure of approximation quality. And yeah, the smaller this delta is, the better our approximation, because, well, when the approximation is very good, this ratio is almost constant unity. One thing you could, for example, consider is the average distance between pairs of vertices. And if you plot that, you see, indeed, there is some correlation here. So the larger this distance is, the larger the period is. This gives you a delta of approximately 30%. So yeah, it tells you something, but it's not actually super accurate. But that motivates us to do something very physical, namely consider the average resistance. To that end, here we take our graph, a completion. We replace every edge by a 1 ohm resistor. And then we could technically build it, but we don't need to build it because people in the 1800s told us how to solve that mathematically. So we compute the resistance between pairs of vertices, which gives you this resistance matrix. And then the average of all the resistances is what's called the Kirchhoff index, or the average resistance between any pair of vertices. And yeah, so besides being physically nice, also this thing correlates quite a lot, which again is relatively surprising to me, given that the period integral is some extremely involved multiple integral over a gigantic polynomial. And it turns out, well, if you basically take the inverse of the Laplacian, you get the value to 5%. So that's nice. And also it's extremely fast, like you can do it in microseconds on a computer. You can do even better if you count cycles. Here is a cycle. Not that anyone here does not know what a cycle is. Well, we count all the cycles, which means not the one that are there like simultaneously. So this is not the loop number or the dimension of cycle space, but it's actually all the cycles in cycle space. And our graphs, being simple graphs, have no cycles of length 1 or 2. And 3 is then the number of triangles, and 4 is the number of squares, and so on. We do our usual plots. We find this. Here is the number of triangles. Here is the period, or the log of the period. Yeah, well, looks not bad. And then we go on. Here's the number of squares and the period. That actually does look bad. So maybe it was not such a good idea. Or we plot it in 3D. And if you look from this diagonal angle onto the 3D plot, so here's the squares and here's the triangles, then you find that actually this thing is a kind of 3-dimensional tilted plane. So indeed, if you do a multilinear function of all the higher cycle counts as well, you get a pretty good approximation. Depending on what the largest size is that you take into it, it gets better and better until approximately length 10. And then you have an accuracy of approximately 2%, which is impressive when you think that instead of solving a hard integral, you just count the cycles. Okay, you can do a few variations on this cycle model. You can, for example, concentrate on the smaller ones because they can be very quickly computed without actually counting. You can also make this generating function of the cycle numbers, which is something like a cycle polynomial. This one, if you plot it, makes this nice plot, so it is also very correlated. But it's just numerically not so favorable. So it makes nice plots, but it's not as useful because you need all the highest numbers. And for the previous one, we only need up to n10. Then you can do the same story with the cuts. So count how many cuts there are. Here's again our 6 cut. Count the 8 cuts, count the 10 cuts, and so on. Make a multilinear function. It works all the same. And you compute, well, the same thing. And you combine it with the cycles. So here is red is the cuts alone, blue is the cycles alone, and black is cycles and cuts in the model. And unsurprisingly, it's yet a little bit better. Okay, so these are the models that are kind of based on counting something. Then we saw these period invariants. I mean, the cuts are a period invariant, but we saw the Martin and the Hebb bound, and clearly we want to correlate them. So here is the Hebb bound, and here is the period, and you see they are very, very closely correlated. So they give you approximately 1%, and if you also include the number of cuts, they give you 0.2. So you can guess the value of this complicated integral to more than 2 significant digits by just computing this Hebb bound, which is some rational number. Unfortunately, this is relatively hard to compute for a large graph, so you need to iterate over all subgraphs. It's not as fast as these counting models. The same with the Martin. So we had this first Martin invariant, which is just the derivative of the circuit partition polynomial. And then we had the higher ones where we replace every edge by k parallel edges. And you can go as far as your computer can. And you see my computer could go until 17 with M2 and until 12 with M3. So they get harder and harder to compute, but also they give better and better approximations. Okay, so that is nice conceptually because, well, it's nice to see that these invariants are related, but it's not so useful to spend hours on computing some higher Martin invariants instead of spending hours to solve the actual integral. Finally, there's also some work on machine learning by Kimia, who's over there. So what I've presented so far was really physically hand-picked models, and we used a lot of physical intuition for that. You can also just throw everything into machine learning, and, well, you get actually a better result, so you get 0.1%. But to be fair, that uses all the quantities, and the previous models only had 1 or 2. So this uses a lot of data, which is hard to obtain in practice. So there is a motivation to give it just the graph and not all these invariants and all these other things. And yeah, we tried that as well. We trained several different models on the graph itself. And it turns out, yes, to some extent they can predict the period, but it's not yet completely reliable. So they tend to be relatively susceptible to outliers and tend to do crazy things when they're trained with somehow the slightly wrong data set. But yeah, we're still working on that, and probably sooner or later machine learning will replace all of this. If you want to try for yourself, the data set is freely available. Download it and try. Okay, so we have seen the period is correlated with almost everything, basically, to some extent. And that is nice because we can get an estimate for the period without actually solving the hard integral. And some of these correlations actually have nice interpretations, for example, these electrical properties, or just the physical size of the graph, like the average distance. Some others are combinatorially interesting, like this Martin invariant, which is evaluation of these partition polynomials. But what is that actually good for? And it is good for something. Namely, we can use it to actually improve our computation of physical quantities. So I mentioned in the very beginning that these periods in principle encode the scale dependence of a theory. A little bit more technically correct, what you want to compute is the beta function, which is the sum of all periods of a given loop number multiplied by their circuit partition polynomial and multiplied by a bunch of more or less trivial factors. Okay, let's think about that at 14 loops. We saw at 14 loops there are something like 100 million graphs. We saw it takes 1 hour to numerically compute one of these graphs. So we don't have 100 million hours, so we can't do that. Then maybe we don't need to compute all of them. Maybe we take a small sample. But we also saw that the standard deviation is approximately 100% the average. So if we take a small sample, the sampling accuracy will scale like this, like 1 over root sample size times standard deviation. And since this is approximately unity, if we want, for example, a 3-digit significant result here, we will need 10 to the negative 3 here, which means 10 to the 6 there. So we need 1 million graphs still. So also taking a sample doesn't work. And of course, the solution is we will exploit these correlations and use weighted sampling to actually sample the graphs not uniformly, but sample them according to our estimated period. How does that work? Well, it works by the law of conditional probability. You take a sample which is weighted proportional to your approximation function. And then within that sample, you evaluate this ratio of the actual period divided by the approximation. Your approximation function is good, so this ratio is essentially unity with very small deviations if your function is good. And then you multiply the same thing with the expectation of the approximation. That has this huge standard deviation, so this is not easy to sample, but your approximation function is fast. So instead of spending 1 hour for each sample on this side, you spend a few milliseconds because you can do that very quickly. It's just counting some cycles or something like that. And the idea is if your approximation is very fast and very accurate, then each of these factors is significantly more accurate than just naively sampling. Yeah, well, that's an old idea. For that, we need our things to be fast. Here is a plot of the speed of these predictions. As I mentioned before, the resistance is extremely fast because it's just some graph operation on the matrix. Then here are all the different models that use counting cycles, counting cuts, counting whatever. Their time grows exponentially, but somehow moderately. And then here are Hepbound and Martin, and you really see they grow much faster because they require, well, enumeration of all subgraphs of a given graph, which is just much slower than counting all edges or something like that. And in practice, we will use this cuts and cycles model, which is one of these lines, I think the blue one, which is somewhere in the 10 milliseconds range per graph. You can also, well, here's a plot comparing the accuracy and the time, and you see clearly the slower models are more accurate. But it turns out that actually here in the middle are the ones that you want to use in terms to balance accuracy and time. Okay, then you write yet another program. This program does a lot of things itself, so it generates the graphs, it determines the sampling factor, so it will produce NS graphs, where NS is something like a few thousand, and integrate only one of them and use, well, all the others just for the right-hand side of this conditional probability equation. And there is a lot of multi-threading and whatnot, and then you let it run for a week. Well, yeah, here is how it integrated its graph per second, and you see there are these dips when other people start something on our servers. That's, I think, what everyone has seen who has ever run anything on our servers. But they are not actually that deep, so it goes down from 74 to whatever, that is 68, so it's still okay. And here's what we get. So this plot is in 1,000 CPU core hours, which is not as much as it sounds. So if you have 1 week at 120 cores, I think it's 25,000 core hours. So this is slightly more than a week actual runtime on one of our servers. This big orange bar here is the previous best estimate, which took 400,000 hours. And you see that we match the accuracy basically immediately after 1 hour or so of runtime. And then it does what Monte Carlo algorithms always do. It fluctuates, but it eventually converges to some value. Well, so we see it's a lot faster than the previous uniform sampling. Here's the same for 15 loops. Again, the previous values were very much broader, and we matched them immediately and let it run for a week and get this much smaller uncertainty. And if you do the math, you find that actually, well, to reach a given accuracy, we are approximately 1,000 times faster than naive sampling. Or if we have a fixed time, then we reach 35 times the accuracy, which is root 1,000. So this is actually a huge improvement. Okay, very last thing. I mentioned this ON dependence, so you can also compute the ON dependent beta function, and it will give you something that is roughly a polynomial. It just grows extremely quickly for positive n, so that's not interesting to plot. What is interesting to plot is what it does for negative n. So we see, well, these are different runs, so that's why there are different lines and different error bars. We see that it oscillates, and it appears to have these zeros at approximately negative even integers. And yeah, they become more and more exact negative integers the higher the loop order you go. I don't yet know why, but that's work in progress. Yeah, also there is no zero at -2, but -2 is exactly this particular point where we compute this Martin invariant. So that's also a physically interesting point. So there's definitely some interesting combinatorics with these, well, with these cycle polynomials going on, and we are working on that together with Johannes Thüring. Okay, that brings me to the conclusion. So we have reviewed quantum field theory in 1 minute. We have seen that we want Feynman integrals and we want to solve them. Unfortunately, there are a lot of graphs, so we can typically not solve all of them. They might have some symmetries, which reduces the count somewhat. And these symmetries have relatively interesting combinatorial properties, and there are still things to be discovered there. We saw that the random graphs G and 4 are a relatively good model, at least for large graphs. We saw that we can give the whole theory an ON symmetry, which on the one hand gives us this wiggly beta functions I showed in the end, but on the other hand, also in evaluating its derivative at -2, it has this combinatorial interpretation of Martin invariant. Yeah, the periods themselves have some relatively smooth distribution, which has very large outliers. And that means that it's hard to sample them in principle, but you can use all these correlations to sample them. That makes it a lot easier. And yeah, we showed some example program to do that for this particular example theory, which is approximately 1,000 times faster than just naively sampling. So there is actually some physical outcome of all this.
What do you sample? From what?
I'm sampling graphs. So yeah, so there's these, in principle, 1.4 billion graphs, and I'm sampling them according to their estimated value.
According to this GN4 distribution?
Yeah, according to these correlations here. So exactly what I use is, well, okay. In principle, I use something like this here. So I count cycles, I count cuts. This gives me this estimate for the period, and I use that as a weighting function to sample graphs. Okay, yes, that's it. Thank you.
Thank you very much for the talk. Are there any questions?
So you said that counting cycles is a good enough estimation for the period, and you can use GND or GN4 to have a good estimation of primitive graph. But we know the number of cycles in GN4. Like it's more or less Poisson and it's large. So can you try to actually use that estimate to get a distribution of the period?
Yes, actually I use this property of GN4. Where is it?
I might have missed it.
I use it here. So for my model, you see, I don't just sum the cycle counts, I normalize them with respect to this GN4. So this is actually an information from GN4 that I input into this model, and that really helps with normalizing these coefficients, because if you don't do that, then you get ugly fit coefficients which are not stable. So this really helps in stabilizing this and making this run automatically. So it actually does that all in itself without manually fitting anything.
Okay. And you use GN4, which is just a uniform, I guess. And have you tried other random graph models? I don't know if...
Sorry?
There are other different graph models of random graph. Like
yeah, there are also other models. I just compared it to GN4 here because, well, that's the one I found useful for this particular one. And asymptotically, well, apparently most or asymptotically all of the graphs in GN4 are primitive, so that's in that sense a good model. But surely there can be more refined models, that's clear. I mean, basically you want to filter GN4 for the internally 6-edge connected graphs and throw out all that are not.
Thanks.
Any other questions?
Is there like any complexity result, like, oh, given a graph in, let's say, GN4, like how hard it is to compute the period or something like that?
I am not actually aware. Let me think. Well, I mean, yeah, how hard it is to compute it analytically is, of course, well, that's, of course, another question. Numerically, I mean, of course, we have a lot of data on how long it takes to actually do it. And I think there are some estimations because, of course, you know how many Hebb sectors you're going to get that this algorithm is sampling from. And then for each of that sampling point, it needs to compute a certain determinant. And we know how long it takes to compute a determinant in principle. So I think this can, in principle, be figured out. I'm not aware if there is any really concrete formula. But I think it wouldn't be too hard to actually find one, because we know really for each individual step how long it takes.
Thank you.
Maybe last question.
So just curious if there is any result about matroids with these Feynman integrals? I mean, physicists presumably know about matroids.
So, yes, there is something about matroids. There is this Hebb bound. So this Hebb invariant, actually, you can also define for matroids. And actually, this paper, where they discuss all the properties of this thing, this is mostly about matroids. So this works in full generality for matroids. Yeah, the symmetries of the period, not all of the period symmetries just make sense for matroids. So there are some which are really like, okay, cut a graph here and there and glue it like this or that, and so far. Well, we suspect that there is some interpretation of this in terms of matroid. It would be really nice, but we haven't really found any concrete way to make that work for a general matroid. Yeah.
Let us thank the speaker again and leave the other questions.